Welcome to The Explainer. Today, we're exploring this really fascinating intersection of architecture, fluid dynamics, and microbiology. We're looking at exactly how engineers build literally invisible fortresses to protect our most critical medicines from the microscopic world.
So let's just dive right into it. How do you actually build a room where the air is perfectly pure so that not even a single microscopic threat can jeopardize patient safety? I mean, when you're producing things like intravenous drugs or vaccines, a single stray bacterium is absolutely 100% unacceptable.
To answer that, we're going to map out what's known as the Aseptic Engineering Blueprint. We'll be walking through the World Health Organization's Good Manufacturing Practice Guidelines, literally navigating from the outer walls of the facility all the way down into the inner sanctum where the medicine is actually exposed.
Now, the absolutely crucial concept here is asepsis. And it's not just about, cleaning a room. It's a meticulous, continuous state of control. The whole goal is maintaining an environment that keeps products perfectly free from microbes, airborne particles, and pyrogens. It's really an active, ongoing defense system. Section 1. Mapping the fortress. Cleanroom grades A to D. Let's get into it.
You can kind of think of this blueprint like the rings of a giant target. We start out in grades D and C. Those are used for the less critical material preparation. Then we step inward into grade B, which is the strict background cleanroom. And finally, we hit the bullseye, grade A. That's the ultra-pure critical zone reserved for the really high-risk operations, like filling vials with liquid medicine.
To give you a real sense of the microscopic scale we're dealing with here, in a grade A zone, the WHO guidelines allow a maximum of just 3,520 tiny airborne particles per cubic meter of air. To put that into perspective, a standard grade D room allows up to 3.5 million of those exact same particles. So yeah, the air in grade A is practically flawless.
And the drop in allowable microbial contamination as you move deeper into this fortress is just staggering. Whether we're talking about microbes falling out of the air or hiding on surfaces, the limits just absolutely plummet. We go from 200 colony-forming units allowed in a grade D air sample to 10 in grade B, straight down to absolute zero in grade A. Literally, no growth is the only acceptable metric there.
Because of those incredibly strict limits, a single solitary viable microorganism detected anywhere in grade A is a complete breach of the fortress. It triggers an immediate full-scale investigation because at that point, the entire process is compromised.
Section 2. Invisible walls, HVAC and airflow engineering.
So if we can't have a single microbe in grade A, how do we keep them out? Well, the facility's HVAC system is really the engine of this defense. It creates these things called pressure cascades. By maintaining adjacent rooms at a minimum 10 pascal pressure differential, the clean room physically forces highly filtered HEPA-quality air outward. So if a door opens, air rushes out, meaning contaminants from the dirtier rooms literally cannot sneak their way in. And just to be safe, airlock doors are interlocked so they can never be opened at the same time.
Now, once you're actually inside grade A, the airflow changes completely. We rely on unidirectional airflow. This means the air moves in perfect, parallel lines, what engineers call first air, at a very precise speed of 0.36 to 0.54 meters per second. It basically acts like a continuous, invisible broom, just sweeping any generated particles down and away from the exposed medicine before they can ever settle.
Section 3. The inner sanctum. Physical barriers and isolators. Manufacturers actually face a really fascinating choice of physical armor here. On one hand, you have RABS, that's Restricted Access Barrier Systems. These give you rigid walls and integrated gloves, but they still rely on a grade B background room for protection when they're opened. On the other hand, we have closed isolators. These are fully sealed systems that can often sit in a lower grade room simply because they're completely cut off from the surrounding environment.
But wait, if it's completely cut off, how do you even get the medicine inside, right? Well, both systems use incredibly advanced transfer technologies, things like rapid transfer ports or sterilization-in-place pipework. These ensure that sterilized materials and liquids can safely enter that grade A sanctum without ever exposing the internal environment to the outside air.
Section 4. The greatest threat, the human variable. Despite all this heavy engineering, there's one massive variable the blueprint has to account for. And, well, that threat is us. Humans are literally walking microbial ecosystems. We shed thousands of skin cells and particles every single minute.
which is exactly why the WHO dictates such incredibly strict limits on personnel inside the fortress. We are the ultimate wildcard.
Because we're the greatest risk, the blueprint mitigates our presence aggressively. You've got dedicated personnel, airlocks, super strict step-over benches for gowning into sterilized suits, and rigorous visual checks of sterilized gloves. Every single time an operator touches the process through a glove port, it's logged as an intervention. In fact, the ultimate goal of modern facilities right now is to use robotics and automation to eliminate human interventions entirely.
Section 5. Stress testing the fortress. Aseptic process simulation.
So you've built the clean rooms, installed the HVAC, and suited up your operators. But before a single drop of real medicine is made for the public, this entire blueprint must be relentlessly validated. This is done through an aseptic process simulation, often called a media fill. Engineers substitute the actual medicine with a sterile nutrient broth, basically a liquid that bacteria absolutely love to grow in. Then they run the whole manufacturing process, simulating worst-case scenarios, maximum holding times, and every possible human intervention. They're setting a trap. After that, they incubate all those sealed vials of broth.
They are hunting for breaches. If even one single microbial colony grows in those thousands of incubated vials, the fortress has failed. Period. Engineers have to find the breach, fix it, and then successfully pass 3 consecutive simulated runs before real production is legally allowed to begin. The standards are absolutely unforgiving. This aseptic blueprint really is a masterpiece of invisible engineering, keeping patients safe every single day. But it leaves us with a pretty exciting question. As our medicines become more and more complex, like personalized gene therapies, how will these fortresses evolve to stay one step ahead of the microscopic world? Thanks for joining me on this explainer. Keep wondering and keep learning.